Hey everyone, welcome to week 3. This week is probably going to be more exciting compared to the previous 2 weeks, and that's because we are going to talk about agents. And agents, probably you've heard the term over the last year. It's very popular, commonly used. A lot of teams or startups or companies are building agentic systems. So we're going to focus on those and also different agency levels. We'll go over workflows and learn different patterns like prompt chaining, routing, parallelization, and so on. Then we'll introduce tools and we'll understand what is tool calling or function calling and tool execution, and also MCP, Model Context Protocol. After that, we'll switch to multi-step agents and we'll go over some frameworks like React. After that, we have multi-agent systems, and a popular example is deep research, which we are going to heavily focus on next week. And then we'll talk about A2A protocol, and finally, we'll go over some available agentic frameworks that we can use to build systems. And after that, we have project 3, which is building an Ask the Web agent. Project 3 is also very interesting because we see in practice how can we really take advantage of all these different frameworks and what we learned to build an actual system, something very similar to Perplexity, and of course a lot simpler, but basically we'll get the intuition and high-level idea. So it's going to be probably an exciting week. Let's start. Okay, so what are agents? Before we define agents formally, basically I want to point out that agents are everywhere these days. Whenever I go to social media, I see agents. I go to YouTube, I see a lot of videos or tutorials or even ads about companies or startups building agents or providing agentic services. Also, there are a lot of ads. Whenever I commute to San Francisco, I see a lot of billboards that are advertising their agentic system. And this is a real example, a real picture from San Francisco. And basically, they are advertising that something like put AI agents to work for people. And there are a lot of similar examples, again, in San Francisco at least. So agents are everywhere, but what are they? Before formally defining it, let's get some intuition. Basically, when we add more capability to LLMs, then we have agents. So it's just a more capable LLM. And of course, with some additional tools and components added to the LLM and some coordinator or software that coordinates all these using different components. But at a very high level, basically, our goal is how to make LLMs more powerful. Because LLMs are static, we saw in the previous weeks. LLMs are just a model trained on internet data, and they know how to predict the next token. And statistically, those predicted tokens are mimicking internet data. So they don't have really any autonomy or agency to plan or perform actions or break complex tasks into subtasks. And we know that these are all things that we desire. If we have a system or agent that can plan or has autonomy or has more agency and it can plan, basically it gives those systems the ability to perform tasks on behalf of users or humans. So now, basically, here is an example. Let's say we have a simple prompt like write an email to my boss to take 1 day off. Now, something like this, if it goes to LLM or advanced LLMs that we have seen in previous lectures, LLMs are very likely to successfully respond to them. And by successfully, I mean they respond in a way that we would end up happy. However, if we ask something like write a full report on housing market and share existing opportunities and pass this to the LLM, it's very likely that the LLM would fail because this prompt is simply too complex for the LLM to solve it. It requires a lot of cognitive load. And then the LLM also requires do certain things in order to answer to this prompt. For example, it needs to search the web, understand what are like how the market looks like, what are some reports, and then after that it has to analyze those reports and then find some trends, and after that share existing opportunities. So it's simply a lot of work for an LLM, which is simply a next token predictor to do all these things. So it would fail. Now with agents, the same prompt, when it goes to the agents are basically built or aimed so that they can address these kind of complex prompts. So it's going to be very useful for people because now we can easily automate more complex tasks and they can just complete those tasks on behalf of users. And there are lots of different examples of agents these days. We have legal agents. Basically, they automate legal research, drafting, and analysis, and so on. And there are some examples of different startups that are building those agents. We have AI sales agents that automate sales and for prospecting, lead, and so on. We have phone agents that automate phone calls to handle customers' conversations end to end. We have also computer using agents. And these agents are using a computer to complete tasks. Basically, they have access to a computer and a browser to complete those tasks. And one popular example is OpenAI's operator. We have also coding agents that are becoming very popular these days. And basically, coding agents perform software development tasks automatically. So they are making software engineers a lot more productive and automating a lot of those workflows for them. And one popular example, again, is OpenAI's Codex. And then we have also some generic agents that can just perform complex tasks for their users. And OpenAI agent is one example. Before moving to the formal definition of agents and more technical definition, let's go to ChatGPT. So this is the ChatGPT UI. And here is, for instance, the Codex. And if you click on it, you would go to this very similar environment. But now the difference is that in this environment, it's basically giving you an agentic system, meaning that you can connect it to your code base or to your Git repo. And then from there, you can just describe a task, and it would just take care of all those software development process. And then it can also send you a pull request. So those kind of things. You can see here it's connected to a repo, and then it has branches, and it has also versionings. So basically, you can just easily say, hey, there is a bug in this branch or with regard to this, and can you find it and fix it? And then this agent would just take care of all of the steps. There is also this operator, which we just saw. And basically, this is an agent that can use its own browser to perform tasks for you. So here you can see an example. Basically, there was some prompt here, and then the agent is opening the browser, setting up the environment, searching the web, and then based on the web search and results, it decides to search or going to more websites and continue searching, or once it has some good results, it would just share with the user. And I know there are a lot of other companies that are working on building similar agentic systems to basically browse on their own. So that's very interesting. And then another agent that ChatGPT provides is basically the generic agent. And here we can just choose agent mode, and it's new, it's recently introduced. And then here we can ask something, and it could be anything, and it would just decides what to do. It would plan, it would search the web, it would use a lot of different tools, and it would try to complete the task for us. So, and it generally takes some time. For example, when you enter something like, can you plan our trip or something, it may take minutes or 10 minutes or 20 minutes or even more. For example, I searched just to see how it works. I searched this agent with something like, can you list 5-star hotels in Bora Bora that are available? We are planning a 5-day trip. I mean, this is just imaginary. We are not going to Bora Bora, but I just wanted to know how capable the model is if I specify certain details or filters that we are hoping to have in our trip. So basically, I'm saying 5 days trip, and we are flexible, and the date range is here. Provide me with the best available options and also flight options from San Francisco. I prefer this and that, and not too long flights, and not crazy expensive, but also something premium and manageable. So here you can see this agent worked for 10 minutes on my behalf. And this is its results. Here are some 5-star hotels, and it's sharing all the highlights and features. And then after that, it's giving me different options that I have to fly to Bora Bora, and then like different options based on what I specified. And then finally, some books and sources. Now, what is interesting is that if we click here, basically it says worked for 10 minutes. And it's basically 5 searches, 44 sources. Now, if I click here, I would see the entire process. And basically, it's incredible. It's just it's setting up its environment, going to browser, searching a lot of different things, opening tabs, and just doing all this stuff. So I think it's just very interesting. So here it's just it's basically here is showing how the agent is thinking, and also some searches that are happening on the background. So here it's going to booking.com and then trying to search for hotels. And then, again, searching. It also sometimes get access denied. Let's see. Okay, and here is in the united.com. It's trying to search for flights for me from San Francisco to Bora Bora. And then it searches again. So obviously, if I wanted to all of this, it would have taken me more than 10 minutes. It would have taken me at least 1 hour or even more to just collect all those information, go to all these different websites, just to figure out simple things like what are different hotels and what are the highlights. But this agent has just did this for me in just 10 minutes, and it just made life a lot easier for me. It's also including some rates and everything. So at least it would be a very good starting point for me to do something. It's just simplifying a lot of the initial exploration and research. And then after that, it would just take me a lot less time to just do my task or complete my task. So these are some different examples that we've seen. But now let's switch to more technical definition of agents. So again, the goal of building agents is basically the main question to answer is how can we make LLMs more capable? So that's the desire. And that's because for certain questions, for example, if we ask how is the weather today in San Francisco, if we ask from the LLM would have no idea how's the weather today if it's not augmented with additional components. And that's because LLMs do not have access to live data or live information, and they can simply just use their internal weights to predict the next token. So in this case, they may just output something like, the weather is this, which is obviously not accurate. Or if they are more smart, they would know that they are not capable of answering this type of questions. So they may say something like, hey, I'm an AI, I am an LLM, and then I cannot just provide live data. And just to get an idea about this, let's go to hyperbolic. Then I'm going to choose the Llama 3.370 billion. And then here I'm going to ask the same question. Let me reduce this to 60. How is the weather in San Francisco today? So again, this is just a model. This is just the instruct model. It doesn't have access to anything extra like different components or APIs or tools. So it really cannot answer these kind of questions. But let's see how it responds. Okay, this model is capable enough that it recognizes that this kind of prompt is not something that it can answer. So it's not hallucinating, which is good. It's just saying that I'm a large language model. I don't have real-time access to current weather conditions. So again, this is very good that the model knows that it cannot answer and it says I cannot. But that's not ideal. Ideally, what we want is that we want a model that can tell us how's the weather. And for this, one possible way to make this LLM more capable is to augment it with some external APIs, like Weather API, that can provide those information to this LLM. There are also other questions, like asking mathematical calculations. For example, what is this plus this? And LLMs are not generally good at these kind of problems because, again, they have some learned weights, and then they use those weights to predict the tokens. And they have not really learned the instructions to make additions or multiply two big numbers. And in order to make LLM more capable for these kind of questions, one way is to just augment it with a calculator tool. And there are lots of different examples. For where is my order, the LLM we should give access to some database for the LLM to answer these kind of questions. Let's say for specialized use cases like a retail store. Or when we have questions like who scored in some game, it requires web search. So we can augment it with web search capability. When we want to write a full report on something, we can augment it with different things, including a memory, adding a memory to the LLM, so it can just refine its answers. Or something like, what is your refund policy? We saw this in the last week, that we can add RAG, or retrieval component, to the LLM. And basically RAG was one way that we can make LLMs more capable. And then it can answer these kind of questions. But there are all these different types of questions that we can, initially the LLM is not capable of answering, but by just adding more components and augmenting the LLM with those components, the LLM becomes capable to answer these questions. Before going to the definition, let's just spend a little bit more time on this kind of calculations to better understand what that means. So again, this is the same model. Now, if I ask a question like, what is 3 plus 3? In this case, it's very likely that the model would output 6, because it has probably seen a very similar example in its training data. Somewhere on the internet, there might be 3 plus 3 equals 6. And then the model has probably learned it or memorized it. So let's see if it can really answer. Yes, it can answer it correctly. Now, if we ask more complex mathematical calculations, like what is this times like this, I don't know if this is really correct or not. Let me use my system calculator. Okay, and this is the... Okay, that's impressive. The model has also done correctly for this multiplication. Now, let me make it even more complicated. Let's see if it can answer this question. And let me copy it here, the correct answer, so we can compare it. So, okay, so this time the model couldn't make it, and it's obviously incorrect. It's close enough, but it's incorrect. So what I wanted to show here is that these kind of questions are very simple for humans, because we have some instructions. We have also access to some tools. I mean, for me as a human to get to solve this question, it was just a few seconds. I had to just search my system and use its calculator to calculate this. And it's also very reliable, because calculator is also implemented such that it follows certain instructions. So these kind of questions are very easy if we are given access to certain tools. And it can be impossible to solve if we are not having access to those tools, especially for a computer or for a LLM. And that's why it becomes very important to provide LLMs with additional tools or components so that they can become more capable. So this was just an example, but we can see very similar things with all these examples. So now let's go to the more technical definition of making LLMs more capable. All right, so what is an AI agent? If I search Google with AI agents, or what is an AI agent, basically there are lots of different links, and many of these links are coming from credible websites or like Databricks and Google Cloud. And they all are having a page dedicated to explaining AI agents and defining them. And many of these are defining differently with different terminology. But all of them are basically talking about something very similar. They overlap. At their core, they are explaining something similar. They're just using different terminologies. For example, Google Cloud is saying that AI agents are software systems that use AI to pursue goals and complete tasks on behalf of users. IBM has their own definition. Microsoft has, what are AI agents? And then I'm sure there are a lot more examples like GitHub, Amazon, NVIDIA, Salesforce. So again, there is not a single correct definition. There are different ways that we can put this into words. But at a very high level, basically an agent is just a software system that uses an LLM to pursue goals and complete tasks on behalf of users. So all those definitions that we just saw on different websites, they all emphasize on key things. So one key thing is that it complete tasks on behalf of users. And the other is that it pursues some goals. And also they basically plan, reason, call tools, and rely on memory to complete those complex tasks. So what that means is that they're given access to different components, and they are also more capable. They can plan and reason. So, and this whole thing can be visualized something like this. Basically, there is agent. This pink rectangle is agent, and basically it's a software. So agent is also a software, but we call it agent because it can coordinate and talking with different components and pieces and services to get tasks done. So we call them agents. Occasionally we may call them software, but again, all that matters is that it's just some software sitting here in between different components so that it can complete tasks. So whenever there is a prompt, the prompt goes to this agent, and the agent has access to LLM, obviously, as the core next token predictor component. So this LLM helps the agent with planning and reasoning. The agent has also access to tools such as calculator, web search, and so on. And these tools are allowing the agent to execute actions. It has also access to memory, to store or retrieve information. They can be also given additional access to more components like RAGs for like retrieval. And then after the agent just coordinate with all these things and orchestrate a sequence of tasks, then once the final output is ready and the agent believes that the task is complete, it would then send the response back to the user. And this entire thing, we can think of it as an agentic system. Basically, we are having a system which this agent orchestrates between these different components. And again, there are different websites explaining what are agents. One example is Hugging Face has this agent course, and they have their own definition. It's an interesting guide. If you are interested to learn more, you can just go to this website. But this is basically an agent. Now, this agent ideally, these agents should have given a lot of autonomy and agency so that they can complete whatever complex task that we have in mind. But that can be very complex in the beginning. So a lot of times what is ideal is that we move like a step by step. So we slowly increase the agency or autonomy of this software. And because of that, there are different levels of agency that are defined. Basically, agents have autonomy, LLMs don't. So the goal is that to slowly give LLMs more autonomy to complete tasks. And there are different levels of giving this autonomy or agency. And they can be divided in this way. And different websites are relying on something like this. So the first and lowest autonomy that are available is simple processor. Again, we'll talk about all these different agency levels in very detail. But basically, the lowest is simple processor. Then we have workflows. Then we have tool callers. Then we have multi-step agent. And finally, we have multi-agent systems. And these are just referring to different, basically, agents with different agency levels. And there are a lot of arguments about at which level we can really say something is agent versus not. And we'll talk about that. We'll talk more about that. But this is the overall picture of different agency levels that we can add to the LLMs. So in the next lecture, we'll start with simple processor, and then we'll switch to workflows. All right. So the lowest agency level in an agentic system is a simple processor. And basically, in this case, we have this software, and it's just it's a very simple software. And it only interacts with the LLM to answer the prompts. Basically, it just samples from this LLM using sampling method like top K. So whenever the user has some prompt, the prompt directly goes to this software. The software sends this prompt with maybe some additional prompt engineering to this LLM. The LLM responds in a generation loop, generate tokens one by one. And then when the token generation is done, the software would output the response. So this is, again, it has the lowest agency level. It's not really capable of planning or handling complex prompts. It only samples, basically model this process as a one-step process. When whatever the prompt is, it just sends it to the LLM, get the response, and show it to the user. So this is not really considered an agent. It's more like a software, a simple software. So this kind of system is more like it's not agentic system because it has lowest agency. And remember, LLMs are just a model that predict the next token. So we have LLM here, and if we want to be precise, when something like this goes to the LLM, like how is the weather today in San Francisco, the LLM would produce the probabilities, and then from the probabilities, we can pick the next token. So basically, all this LLM, all the LLM does is just outputting the next token. So in practice, there is this loop where the software just interacts with the LLM and generates the final response. And there are more things that are happening in this software. For example, tokenization, how to go from this text to a sequence of IDs. Also prompt engineering, also making sure that the input to this LLM is following the template that this LLM was trained on. So all these are happening by this software. And a lot of times in the lecture, for simplicity, for visual simplicity, we may show that this sentence goes into the LLM and the LLM output the final sentence. And that's more only for visual simplicity. In practice, we always need to have a software that is interacting with this LLM to generate text. So this software looks something like this. Again, it's just a function, and it starts from the messages, like the user prompt. And then it apply this chat template, it gets prompt text, and then it converts them to token IDs. And then here is the main loop to generate text token by token. And then it just keeps doing this. And whenever the stop token is reached, it's breaking from this loop. And then finally, it decodes the IDs back into the generated text. And then it would show it to the user or return it. So that's the lowest agency level, simple processor. In order to make this setup a little bit more complex and make our agentic system give it more agency, next we have workflows. So workflows, basically, the idea here is that an AI workflow is a fixed series of steps. So whatever the specific task is, we can come up with a sequence of steps like this. And it's a predefined. It's basically just a predefined workflow that is implemented by the developer. And this specifies how the information flows. So whenever the prompt comes, basically it follows this fixed set of steps and sequences. And each of these basically can be an LLM call or just some classical code steps. It can be machine learning models. It can be some heuristics. But basically, there is this logic where the information flows. And some of these might be LLMs. So basically, the developer designs a predefined code path and implements an orchestrator to just orchestrate this flow of information. And then at runtime, there is no planning involved. There is not an agent that plans depending on the prompt. The plan is already kind of predefined by the developer. All needs to happen is that an orchestrator just passing the information through this workflow. So basically, each step is executed in a known and deterministic order. And each of these steps can be LLM calls. They can be classical code steps or some heuristics. So this is workflows, and they are very powerful. And there are different patterns to create these workflows. So if you look at all different these workflows that are available out there, all of them can be categorized into these 5 patterns mostly, and there might be some other patterns, but these are very popular patterns for workflows. We have prompt chaining, we have routing, parallelization, reflection, and orchestrator workers. So we'll go over each of these in more detail to understand how can we really build AI workflows that are more capable than just LLMs. So let's start with prompt chaining. The first pattern that we would explore is prompt chaining. It's a popular pattern to build AI workflows. So, and here's the idea. For complex tasks, a single prompt can overwhelm the LLM, meaning that it would add a lot of cognitive load to this LLM that the LLM is no longer able to answer correctly. It may neglect part of the instructions. It may face context drift, meaning that the LLM would at some point may lose track of the initial ask or context. We have also the problem of error propagation, meaning that to answer these, to address these tasks, there is a sequence of steps or reasonings that are required. And at some point, the LLM, if one step has some errors, it just propagates to the next steps. So during the generation, if the answer is going to be too long, just because it requires multiple reasoning steps, the errors would just propagate and accumulate. So by the time that the user would see the final answer, there is a lot of error. Also, the model may hallucinate because of this increased cognitive load that is just provided to the LLM in a single prompt. Imagine one example. Let's say we want to build an agentic system to do market research, and basically it's capable of completing market research tasks. The common normal request or prompt can be something like this: analyze housing market, summarize findings, identify trends, and share current opportunities. So it's something very typical if somebody wants to learn about certain market and find the opportunities. However, this prompt can be very complex for this LLM because there are lots of things that the LLM needs to do. And again, inherently, these LLMs are not capable of doing planning or reasoning. So something like this, it would be too much for the LLM. And that's the idea of prompt chaining. What prompt chaining proposes is to decompose these kind of tasks into a fixed, simpler subtasks. Basically, instead of having one LLM to process the input prompt and generate the response, if we know ahead of time that the nature of our tasks is about market research, we can come up with this workflow and we can decompose the task into 3 steps, let's say. And these steps are basically processed sequentially. So the output of one step is basically going to as the input to the second step. And then for each step, we have certain prompts, and we use those to just chain the output of this into that prompt. And then we pass the new prompt to this LLM. And we'll just keep doing this and following this workflow sequentially. And the final output, which is the output of the last LLM, is the final response that we can show to the user. And this can be very powerful. If it's designed carefully, basically it can engage in requests or tasks that require multi-step reasoning and planning. Because ahead of time, we are just planning ahead and coming up with this workflow of the required multi-step planning that is required for this particular task. So once we have that, basically this workflow is now capable of addressing more complex tasks. Let's see the same example. We saw the prompt like analyzing the housing market and summarizing findings and so on. Now, in this workflow, we can easily answer those questions. So whenever the user query comes, which is supposed to be around doing some market research around some topics, we can build the prompt one, something like this: analyze the market specified in, and then we have user query here. So basically, whatever the user query is, we would just place it here, and we construct prompt one. And this can be done automatically, meaning that the same software that we just showed can just build this prompt. And then this prompt now goes to LLM. And this LLM at this stage is only responsible to analyzing a market and nothing more. It's not responsible for any summarization task or identifying trends or sharing opportunities. It has only one single responsibility, and that's just analyzing a particular market. So it's a lot simpler task. It doesn't really require multi-step planning or reasoning. And this LLM would output something. And then we can construct the second prompt. We can have something like summarize findings in output one, which is the output of this LLM. Again, the software would construct these prompts and chain all these things and take care of orchestrating this setup or this workflow. So we don't have to worry about that. That's the entire purpose of building these workflows. And now this prompt 2 goes into the LLM. And the LLM would, at this stage, is only responsible for summarization task. So it's a lot simpler task. And most of the times, good LLMs can just handle those kind of tasks. And there is some output. And now at this stage, basically, we tackle the third task, which is identify trends. So whatever the output is, we construct prompt 3 as identify trends in output 2. And then finally, we just keep doing this. The fourth step is prompt 4, which is share opportunities given output 1 and output 2. And we pass these two outputs to this LLM. And basically at this stage, still the LLM has a simpler task because it doesn't have to worry about analyzing the market or summarizing it. Those are already done in previous steps. So this LLM is basically just needs to look at these two outputs in its context and try to find the opportunities and share them. So again, by carefully designing these kind of workflows and doing prompt chaining for tasks that are possible to do prompt chaining, we can build some AI workflows that are more capable. Now, where to use prompt chaining? Basically, we can use prompt chaining in tasks that can easily be decomposed into fixed subtasks. And remember, we are trading off latency for accuracy. We are not getting this increased accuracy for free. Basically, we are having more LLM calls, and that means that more cost and also more latency. It takes longer to process the user's request. But instead, we get better accuracy because now each LLM has a lower cognitive load and can address simpler tasks. And also in cases where we want enhanced reliability, because now we can easily monitor the output of each step and see if something goes wrong, we can see where the problem is happening. And in general, it's expected that the overall output is going to be more reliable. And there are certain examples that prompt chaining is typically used and a good fit. For example, in content generation workflows. Imagine we want to generate some content like an article or some chapters in a book. We can basically decompose it into some steps like writing an outline of a document. So that could be the first step, the first thing that the LLM does. And then the next step, once we have the outline, we can basically check that the outline meets certain criteria. And finally, we can have another LLM, the last step, to write the document based on the outline, step by step. So content generation workflows are a very good example and fit for prompt chaining. The other example can be data extraction workflows. And that's because a lot of times to convert an unstructured text or data into a structured format that we want for our, let's say, internal use, basically it's a sequential process. There are a sequence of steps that we typically go from unstructured data to something in a very structured format. So those tasks are also ideal for prompt chaining. And another example I have here is for information processing workflows. And again, very similar. A lot of times when we have some information or data that we want to process, it has to go through certain number of transformations. So the first step is we transform the raw data into something, and then we keep transforming and transforming. So these are also good examples for using in prompt chaining. And these three are just some examples. I'm sure there are a lot of other examples that prompt chaining can be very useful and make it a lot simpler and easier. So that's all about prompt chaining. Now, the next thing that we are going to talk about is the router or routing pattern. So routing is the second pattern that we would learn for AI workflows. And basically, the intuition here is that for complex tasks, a single LLM may not be good enough to handle different purposes or tasks. And here in routing, we want to go beyond just deterministic sequential processing that we saw in prompt chaining, and we want to introduce conditional logic. And the workflow has two steps, the routing workflow. The first step is first we analyze the incoming query, which is the user's prompt, to determine its intent or its nature. Once the router determines the intent of the prompt, then it can direct it to the specialized branch. And each of these branches are basically specialized, let's say, LLMs that are very good at that particular task. So as soon as the router determines what is the intent of the prompt, it just sends it to that particular LLM, which is really good at handling those kind of requests. And then that final output, the final output would be coming from the chosen branch. In this case, the solid line is showing that this LLM was chosen. Now, let's talk a little bit more about these two and see how can we really build this router. There are different ways routers can be built in practice. The simplest way is we follow some rule-based methods. And basically in rule-based methods, we have some predefined rules or logics to determine the intent of the prompt. It can be just a bunch of if-else statements. And based on those, we can determine which branch should we send this request. The other, a little bit more complex approach is ML-based. And basically in ML-based methods, we employ a traditional machine learning model. It can be a discriminative model that is capable of classifying the intent of a given text. And then based on that machine learning model's output, we can then choose the correct branch. The third approach, which is a little bit more focused on semantic routing, is the idea here is we use something similar to what we learned in the RAG week. And here we want to use some embedding models that are good at converting any text or query to some numerical vectors. And then the way that we build this router is that when the query comes, the user's query, we use the same model to get its embedding. And then the embedding is compared to the embedding of all these different branches or topics. And these embeddings are computed beforehand. It can be based on the topic or the way that this logic, this workflow logic we have in mind or is implemented. And then once it's compared, the embedding of the prompt to embedding of different topics, we can choose the most similar topic and then route this request to that particular branch. And again, this method is more useful for semantic routing because based on the semantic meaning of the input prompt, the router can choose the branch. And then finally, we have LLM routers. So here, basically, the idea is just use another LLM and give it the responsibility of the routing. And it works generally quite well in practice. And what we do here is we just prompt the LLM to classify the intent of this prompt from the list of, let's say, given prompts, given intents. So these are different ways that these routers can be built. And also, regarding these specialized branches, they can be LLMs, but they don't have to be LLMs only. They can be just traditional models, machine learning models that are good at doing certain things. They can be also humans or some manual work. Imagine when the router believes that the prompt requires escalation, it can just send it to some manual department for manual verification or escalation. So again, these branches can be LLMs or they can be other things. So this is routing. And then the next thing is when to use routing. The routing pattern is typically preferred when we are dealing with tasks that can be, we can think of those tasks as distinct categories that are better handled separately. And also for those tasks, we also need to make sure that we can classify the intent. So classification should be also handled accurately. And for those kind of complex tasks, routing workflow works very good. Some examples are, for instance, building customer support agents. And the router first determines what is the intent of the request. It can be a general question. It could be a refund question, refund request. It can be technical support. It can be escalation and so on. And then depending on that, the router would just send it to that particular specialized LLM that is really good at handling those kind of requests. For example, for where is my order, the router believes that the category is shipping, so it would just route it to the shipping LLM. There are also other examples that routers are generally used. And one very important purpose of using routers is for efficiency. A lot of times we can use this setup, this workflow, to route requests based on their level of complexity. For example, if there are easy or common questions, we can just send them to smaller models that are more efficient and faster and less costly. And for hard or unusual questions, the router can just send them to the most capable model that we have. So this way we can optimize cost and speed. For example, again, for simple questions like where is the capital of some country, it's an easy question. So we don't really need to use, for instance, OpenAI doesn't really need to use its best thinking or reasoning model to answer that. It can just use its most efficient, the smallest model to answer that question. All it needs to have is just a simple router. So in case those questions are coming, it doesn't have to just pass it to the very complex and capable models. So this way they can optimize for cost. So that's all I wanted to share for routing. The next pattern that we would talk about is reflection. So what is reflection? It's also called evaluator optimizer, or you may see different terminology here. But basically, the intuition is that the LLM's initial output might not be optimal or accurate, or it might be incomplete. In previous workflows that we've seen, if LLM generates something that is not correct or that's not optimal, there is no way that the workflow can fix that. The purpose of reflection is to address that limitation. Basically, reflection puts generation and evaluation in a loop. So there is this feedback loop, and then there are two components, a generator and an evaluator, or it's also called critic. And the idea is just to put these two in a loop. The LLM generates something, the same LLM evaluate the solution and provide some feedback. And this LLM, again, relies on the feedback and the initial solution to propose a different solution. So this loop basically keeps going until, let's say, this LLM feels that this response is complete and correct, and it can end the loop and then generate the final response to the user. In other words, this reflection is a form of self-correction or self-improvement, because now we iteratively refine the output based on some feedback. And the feedback is coming from the same model. So that's the idea behind reflection. It's more, it makes the workflow more dynamic instead of following a very static, fixed workflow. So this loop goes as long as needed, and it determined at runtime dynamically based on when the LLM feels that a response is good enough. So let's talk more about each piece, generate and critic. Again, you might see different terminologies online, but basically the idea is that this LLM is just responsible to generate. So it has a very clear responsibility. It processes the conversation and generate a correct solution. That's its goal. That's its final responsibility. And in order to do that, it often helps a lot if it keeps a memory of the past interactions or the previous conversation. So basically, starting from the first solution that it proposed and the first feedback that evaluator provided, all the way to the most recent N-1 solution and feedback. So that basically creates the memory of this LLM. And by memory, it means just we include all this information in its context and then just pass it as the input. So the LLM just generates some solution. And then the evaluator or the critic LLM, its primary responsibility is to examine the proposed solution by this LLM and identify the potential issues or flaws and provide a feedback. So basically, it checks for things like factual accuracy, coherence, completeness, instruction followings, like adherence to the instructions, and so on. And one more thing I want to note here is that a lot of times in practice, it's better to employ two specialized LLMs than a single LLM. Although one LLM can just take care of both and have both these responsibilities, we can just have a different prompt. For example, when it's time for generation, we can say, hey, you are a generator. And when it's time for critic, we can say, you are a good evaluator and your responsibility is to evaluate. However, if we use two specialized LLMs, it usually works better. And that's because it basically there might be some bias if the same LLM tries to evaluate its own proposed solution. So this way, by separating these two as two different LLMs, the evaluation would be less biased and also more robust. So this setup would generally lead to more robust responses. So that's all about reflection. And then when to use reflection. Reflection is good in tasks where we have a clear evaluation criteria. And also, we know that iterative refinement helps. Even the analogy would be, for example, a writing task for humans. Humans write something, and then they read it and evaluate it. They find places where it's not written well. Then they try to make it better or rewrite it. So for those kind of tasks, reflection usually works a lot better compared to other patterns. And examples are, for instance, code generation. evaluator run tests and identifies errors in the generated code by the generator. And then the generator write code and try to fix those errors. And there is this loop until at some point evaluator feels that the generated code is now good and complete. Another very popular example is when there are tasks which require complex searches. So a lot of times we have tasks that require multiple rounds of searching and analyzing different websites and so on. So in those tasks, also this reflection setup is usually very helpful because evaluator decides whether further searches are needed based on some collected information and solution. And then the generator performs more searches if needed and collects more information. And there is this loop until evaluator at some point feels that the collected information are sufficient to be shown to the user. And again, another example is creating detailed plans because it requires lots of planning and multi-step reasoning and strategy. So in those tasks, also evaluator decides if a proposed plan has flaws or it can be improved. And then the generator improves the plan based on that feedback. So these are some common examples that reflection pattern is usually very helpful to build AI workflows. But again, there are also other types of workflows. After this, we are going to talk about parallelization. So parallelization is another pattern to build AI workflows. And the idea in parallelization is very simple. For some complex tasks, we can simultaneously process some of its subtasks. So if a task perhaps has multiple subtasks, we can simultaneously have branches and process those subtasks. And then after they are done, we can programmatically aggregate the results using a component, let's say, called aggregator. So basically, for a question that comes here, the subtasks can go to different 3 branches, let's say. Each of these branches would simultaneously work on their own task or subtask. They would use tools, search web, collect information, and then generate some output. And then the aggregator would just look at all their outputs and try to aggregate them and generate the final response. So this setup, this pattern is more efficient because there is no sequential processing involved. Basically, we don't have to wait on one task to be complete in order to start another task. Everything is happening in parallel, and simultaneously these branches are working all together at the same time. So it's generally more efficient. And another value that parallelization often brings is robustness. And that's because a lot of times the same prompt can go to these LLMs. So we don't have to necessarily divide it into subtasks and then pass it to LLMs. We can just pass the same prompt to these LLMs to do some sort of, let's say, research on the web. And then basically the aggregator then can look at all their results and generate some final response. But for validation, basically, if one of these branches did something wrong, let's say LLM have failed to do right researches or miss some information, the aggregator would figure that out because other branches are including those kind of information. So this setup can be also helpful to validate different solutions and generate one final response. And there are 2 variations in parallelization pattern. As I just explained, basically one is sectioning and the other is voting. Sectioning is we break the task into independent subtasks and then run them in parallel. Voting is when we run the same task multiple times to get diverse outputs and benefit from validation. So for example, sectioning, let's say we have a question like, help me learn about Gen AI and RegSys, recommendation systems. In this case, let's say one LLM, one branch can process the request for Gen AI. It goes, searches the web, collect information for Gen AI, and create some output. And then another branch would focus on recommendation systems. So this way, basically, things are more efficient. Basically, we have 2 parallel efforts going on, one for Gen AI, one for reg systems. So it's faster. And for voting, basically the same question, let's say research and give me summary of current state-of-the-art image generators. Now, in this case, the same prompt goes into 2 different branches, and each branch tries to solve this task and collect information and generate some responses on their own. So the benefit of this voting setup is that if one branch is missing something or doing something wrong, the other branch might capture that or not miss that kind of information during its own research. So these are two variations of parallelization. And then the last thing is when to use parallelization. Sorry, this has to be parallelization. Basically, we can use parallelization in tasks where we can divide them into subtasks, and we can then parallelize them for speed. The other scenario where parallelization is helpful is when we want multiple perspectives or attempts for a certain task. And basically, this means that we would end up having results with higher confidence. And that's due to the validation mechanism that we just discussed. So some examples or some scenarios where we can use parallelization to build workflows is research. A lot of times when we want to research and collect a lot of information on the web about the topic, it often helps to have parallelization, have multiple LLMs or even agents working on addressing that question or collecting information. So it's a lot faster. And also if one or two branches miss some information or hallucinate, the other branches are likely not to suffer from the same issue. And then overall, the aggregator would be able to generate something that is correct and comprehensive. Additionally, for use cases like information gathering or multi-API interactions or tool callings, parallelization is helpful. So let's say we have a prompt that requires a lot of requests to some external APIs or using a lot of tools. So these requests, these API requests to external services might be slow and has latency. So by parallelizing these kind of problems, basically we are trying to make things faster by in parallel processing and sending these requests to different APIs. And then finally, for code generation, let's say we want to review some code for vulnerabilities. And that's because, again, for the same code, we can just create multiple branches and send a code to each branch. And each branch is responsible to figure out on its own if there are some vulnerabilities in that code. And then finally, the aggregator would be able to just combine all of them and generate some final list of items to the output. So this is parallelization. Also, there are other patterns which we are not going to go into the detail, but there is this website published by Anthropic, and they're having also a good discussion over workflows versus agents, and we've discussed most of their patterns in workflows, but it's also an interesting read, and there might be some other additional workflows that they are talking about. For example, they have orchestrator workers. So you can take a look at these. These might be a little bit less common compared to what we discussed. Those are the most popular patterns that we talked about. But again, there are also other patterns, and they are designed for different purposes. And then finally, they have also this evaluator optimizer, and then they talk about agents. So that's an interesting article to read. And then the other thing I want to share is that there are also lots of different good resources or links out there to build these. And this is, you would see how it looks like in practice to build some of these workflows. So it's still under Anthropic codebook, and it talks about different workflows. And then there is some actual code. You can see basic workflows, how you can build them. We would also see some examples in project 3 to actually build some of these workflows. So that's all about workflows. In the next video, we'll switch our focus to the third level of agency, which is tool calling or tools. Hey, everyone. We'll continue talking about different agency levels when building agentic systems. And then the third agency level is tool caller, or the ability to call tools. In the last lecture, we talked about workflows, and we saw that how we can follow certain patterns to make LLMs more capable by making multiple LLM calls instead of one and creating a fixed workflow. However, still with those workflows, the agentic system cannot really answer certain types of questions. For example, we also saw that for questions like, how is the weather today in San Francisco? some mathematical questions, or some questions which require live data, for example, who scored in Barcelona game today, the LLMs won't be able to answer those questions. And that's because simply they don't have access to the world, to the web, or to other tools. All they have is some internal weights, which they try to predict tokens one by one. And then even with workflows, still they would fail with answering these questions, because even workflows is basically multiple LLM calls. And different patterns, including reflection, they won't be able to answer these questions, because it doesn't matter how many times the evaluator evaluate the generator's response for the weather. Both of them has no idea about what is the right answer. So Toolcaller basically tries to fix this issue. It tries to make these LLMs more capable by augmenting them with tools. So let's understand how that happens. Basically, at a very high level, we have this software here we saw in also previous agentic systems that we were discussing. We can also call this agent, but let's just say it's a software. And then the prompt comes here. It has access to the LLM. Now, one thing that we add is we give it access to tools. And then based on the LLM and tools, the software makes some arrangements and coordinate between these two and make sure there is some enough back and forth between all these different components. And then it responds. Now, this is too abstract. We will talk in more detail what does it mean to introduce tools. But before that, let's see a real example. For example, when there is a question like, what is this number plus that number? It goes to the software. The software starts talking with the LLM. And then the software would also recognize that this kind of prompt require accessing to certain tools. And after communicating with LLM, it believes that the calculator tool is the best tool for this kind of prompt. And remember, these tools are basically multiple things. It can be a calculator, it can be web search, it can be some APIs like Weather API. It can be some giving it access to some internal databases and code interpreters. And there are lots of other different examples of tools. But in this case, the software believes that the calculator is very useful. It talks with the LLM. The LLM says to the software, hey, use the calculator and pass these two numbers and tell me what the response is. And then as soon as calculator returns the correct answer, the software again talks with the LLM, and then finally it would output the final answer, which is obviously correct because now it's using very specialized tool for this particular question. But again, there are lots of open questions now, which we are going to talk about in this video. For example, who execute these tools? There is this calculator tool. How can we really execute it? Who decides which tool to use given a prompt? How are these tools defined? And so on. So all these questions we would cover shortly. This is the tool calling workflow. There are 3 steps involved. First step is we define a tool. First of all, the first step is basically we ensure that there is something out there that we can use it. Or if it's not, we have to define it. After that is when we let the LLM know about the tool. And that's the second step, because if the LLM has no idea about the existence of these tools, it won't be able to use them. So we'll see how we really let LLM know about that. And then the third step is now when LLM wants to use it, there should be some way to execute those tools and get the correct answer. So that's the step 3, which when LLM wants to use it, there should be some procedure to call the tool and return the response. So let's start. Let's use a real example. And for example, let's say we want to introduce a simple addition capability to an LLM. And ideally, what we want to do is we want to add a new tool to this LLM, augmented with that tool. We call it addition tool. And then when questions like this come, like what is this plus that, the LLM should ideally realize that it can use the tool, it use the tool, and then get the response back and then output. So let's just see for this simple example what these steps look like. The first step is defining a tool. Defining a tool is very simple. All we need to do is we need to write a function, a Python function. And then in the function, we can do the thing that we want to do. In this case, it's just addition. So we write a function like this, def add, and then it has 2 arguments, x and y. And then it outputs x plus y. And it's going to be always correct because we are programmatically calculating this addition. So it's no longer an LLM prediction or using some learned weights to make those kind of predictions. It's very accurate. So now we call this Python file add.py, and there is this function add, and it's clearly adding two numbers. So that's the first step. We define the tool, it meaning that we are just writing a function. So that's why a lot of times there are different terminologies for between function calling or tool calling, because tools at their core are basically a function. So let's go back here. This is a step one, which is very straightforward. Now, step two is when we have to let the LLM know about the tool. Now, before we see this, let's go to a real example. Let me copy paste this. So again, let's go to hyperbolic. We stick to llama 3.18 billion. And in the prompt now, instead of saying what is like two very large numbers, so I don't know really if this answer is correct or not. We can verify it. But now let me enter this prompt as the user prompt. So it says you can use a tool called add to add two numbers. It takes two inputs, number one and number two. It returns their sum. Use it like this. So we have this tool, a special token tool, or this kind of a special format for the LLM to communicate that I want to use a tool. And then here is basically the name of the tool, which we explained here. The name is add. And then these are the two input numbers that we explained here it expects to receive as input. And then after that, it basically closes the tool tag. And here we say just replace N1 and N2 with the numbers you want to add. So now this is part of the prompt now. Basically in the prompt, we are just explaining some tools to the LLM and how to use it. And after that, then we include our question. So for example, here I can say now what is this plus this? Now, what I expect is that the LLM should learn from this kind of question that it can rely on its add tool. And then it outputs something like this. And also from this prompt, it should extract these two numbers and replace N1 and N2 with these numbers. Let's see if it really does that or not. And in the meantime, let me also find the correct number of these two from the calculator. So this is the correct number, just for our reference. So this is incorrect. So initially, the model was outputting the addition incorrectly. This is not equal to this. Now, with this new prompt, it says, let me use the add tool to calculate the sum. So it correctly realized that it can use this tool. And then it says tool, add, and then it's including those two numbers. Again, in this case, it just continue printing something, but we'll talk about that, how to stop the generation here. And as soon as the model, the LLM believes that it can use some tool, we stop the generation, we use the tool, pass this inputs to the function, get the response back, and pass the response to the LLM to continue the generation. We'll talk about that in a bit. But what is interesting to see here is that the model was able to realize that it can rely on this tool for this particular prompt. Now, if I include the same instructions here, and then I ask something very irrelevant, like how is the weather? The LLM is probably no longer going to use any of its tools because it's just irrelevant. The usage of this tool is not going to help to answer this question. Let's see if that's really the case or not. Okay, again, it's not really using any of those tools that we just explained to it. It says, I'm just a large language model. I don't have access to real time and so on. So there is no really using any tools. And by the way, I'll use the add tool to answer your original question about the sum of two numbers. Okay, this is something different, and I forgot to reduce the max tokens, so it just keeps going and going. But again, we basically saw that we can easily explain to the LLM in the prompt that, hey, this is the tool, this is how you can use it, and feel free to use it when you want. Now, we in previous week, we saw that each prompt has two parts, has system prompt and user prompt. System prompt is basically what we define once, and we expect the LLM to rely on those kind of prompt every time there is a request. And then user prompt is basically what the user wants to know or learn about. It's basically the user's query. So a better way to structure this is that instead of including this in the user query, which is not really practical when we, each time we have a question, we include this, what we can do is we can just copy paste this into the system prompt here. So now in the system prompt, basically we are just explaining that every time there is a question, the model would have this system prompt as part of its input. Or let me actually refresh again, and then I paste this here, I reduce this, and then I'd say what is, do I have it? No. What is this plus this? Now, even though there is no longer any explanation of tools in the user query or user prompt, it would still very likely use this tool because it's already present in the system prompt. Okay, it's exactly outputting what I wanted. It just says use the tool, and this is how you need to call it, and then it stops here. So let's now back to our lecture and see the second step. We already saw that in a real example. In this step, we just include the tool and tool usage and the expected inputs or the name of the tool in the system prompt. And then from this point forward, the LLM is aware of this tool. So whenever there is a relevant question, which it believes that the tool can help, it would just use the tool instead of trying to guess the answer. So this is the second step. We write the tool, we explain the tool to the LLM in the system prompt. Next is, now when LLM wants to use it, it calls the tool and returns its response. So basically at this step, we have the user prompt ready, which is the mathematical calculation request. We have also the system prompt here ready, and it's provided to the software. Now the software starts sampling from the LLM, token by token. So basically it passes system prompt and user prompt to the LLM, and the LLM starts to generate tokens as normal. However, the difference now is that the LLM is aware of this system prompt and this tool functionality. So at some point, it may produce this special token tool as its output. And then it says, okay, call this function, and these are the arguments. And then it closes the tag. At this point, the software would realize that, okay, the LLM is definitely needing to call a tool and gets the response back. So at this point, the software stops the generation loop. And it parses this response. It extracts this part, which is the tool calling. And from this part, the software recognizes which tool to call. In this case, it's add. And it also knows what are the arguments. So now the software can easily call that function, which is just a Python file. It would call add, has these two numbers. This function would be called, and then the function would return the accurate and correct response. And then from this point forward, now the software has this, and it sends it back to the LLM. Now LLM knows that the answer is this, and then after this is this number. The LLM knows that this is coming from the tool call. And then the LLM continue to generate tokens one by one. And then whenever the generation is complete, there would be something like the answer is this. So this is the third step of calling functions and giving LLMs the ability to call functions and augmenting them with tools. So we saw all three steps of tool calling. All right, we saw how easy it is to introduce tools to the LLM. We can just explain it in the system prompt. Now, let's just go one step further and try to add more tools. If it's that easy, so it's great. We can just explain more tools in the system prompt, and then we'll basically just simply the LLM would become more powerful. So we saw this example. We saw when we have system prompt, we say to use this tool, how it would use it. Now, let me also add one more tool for getting better. So let me rerun this. And I have this already here. I'll paste it temporarily here so we can easily read it. So basically here I'm saying that you can use a tool called add two numbers. So this is basically the same one as we had before. And now here, I'm also explaining it in plain English that, hey, additionally, you have another tool called get forecast. It takes latitude, longitude, and returns the weather forecast. The args are lat float and lot float. It returns a dictionary of weather predictions for the next few days. You can use it like this. And then here, I'm basically saying, say that you want to use tool, and then here, close it. And this is the function. And these are the two arguments. So I'm going to now remove it from here because it's already in the system prompt. I'm going to now reduce this to 60. And now let me ask questions like, first, let's start with something very generic. Hi, how are you? I'm doing well, thanks for asking. So it's not talking anything about, it's not really demanding any tool usage at this point. By the way, it's interesting because here it says, by the way, it looks like you have some tools available. Generally, with more capable models, these things are not happening. Like if we switch to something like 405 billion parameter models and so on, these things are less likely. But it's also not, bad here. In this case, it's just saying that there are some tools if you want to use it. So for generic questions, it's not desiring to use tools. Now let me say, what is this plus this? You can use the add tool to calculate the sum, and then here it's just outputting its desire to use this tool. And then at this point, again, it's just hallucinating because it doesn't have access to tools. But if we modify the generation loop, this usually won't happen because after this part, the generation would learn about this. It would run the add tool, get the response back, append it to here, something like this. Hey, this is the response. And then when it passes this response and continue the generation loop, then the LLM would be able to correctly print the correct answer. Now, let me also ask a question about weather. How is the weather in San Francisco today? So now, again, this is tricky because the way that the tool usage was defined was based on latitude, longitude. And here we are asking a question about a city. So let's see if the model can really handle this or not. In general, it should be easy to know for popular places what are latitude, longitudes. Also, more capable models, they are generally able to go from some city or county or even a smaller like neighborhoods to the correct latitude, longitude by using other tools like web search. But let's see what it does here. You can use the get forecast tool to get this San Francisco, which is located at here and here. I don't know if this is correct or not. And I think it stopped the generation. So probably it's because it's 60. If I change this to like 90 and ask this question again, it's probably going to complete its answer. All right, so it says, hey, use this tool. And again, that's all we want because then the generation loop can just use the tool. So now we are easily allowing this LLM to use two tools. But remember, this system prompt is becoming more and more complicated. Basically, I just need to explain in plain English that, hey, these are the tools. I can, like however I want, I can just explain it. And then it's just getting more and more and more complicated as we want to introduce more tools. Now imagine I want to introduce the third tool or fourth tool. Each time I have to go to the system prompt and add something else. And if another person wants to also introduce these tools, it's very likely that they would basically explain it in a different way. It's going to be very, very subjective. Basically, each person would have their own kind of tone and language to explain something. So it's not really best practice. It's not a standard way to do this. Now, we saw this example and demo. Now let's go to the lecture. So with more tools, as we saw, we have a weather API. So we can simply add this weather API and let the software be aware of it. And the first step was to defining the tool. Here we have this function, get forecast. And then it's relying on some external APIs from api.weather.gov. And then from there, it's getting the points. And then from there, it's getting the actual forecast and then returning it. So now we have this function. We have to write it as the team or as a company that we want to make our LLM more capable to rely on getting weather information. We have to write this function. And after we write these two functions, we can, as we saw, we can just add it to the system prompt. Then whenever there is a question like this, the system would be able to handle that. And again, we can add more tools. We can add web search tool, and it's still very simple. And web search is very powerful. It suddenly makes the LLM a lot more powerful because it suddenly has access to all the live data available and going on in the world. So a lot of times when we need live data or we need more context, the LLM can decide to use search tool to search the web with a query. So these are all different tools that we can add. But again, we saw that the system prompt keeps getting more and more and more complicated. And also the way that we explain this, it's going to be very, not in a standard way. Different people would explain differently. So it's very messy way of augmenting LLMs with tools. And here is when this whole concept of standardization or standardizing this process comes into play. Basically, the idea is manually creating the system prompt from each tool is not scalable, it's not best practice, and it's not a standard. So we may want to provide the LLM with hundreds of tools at some point, and really explaining each tool in the system prompt can be super annoying. As we change our models, we have to write those system prompts and write those explanations again and again. And it's just not really easy and a scalable way of doing this. So what can we do to make this more standard? Basically, there's this concept of auto-formatting, and it's very simple. The idea is that we all agree and come to an agreement on how to write these functions or write these tools. And then if we all agree on something and make sure we always follow those particular formats or structures when we are writing tools, then we can automate this process. We can write a piece of software here, we name it auto formatter. And basically it's responsible to look at this function definition and extract the explanation of, extract basically the important information from this function, and then output a textual description or explanation of this function. And basically, that's exactly our goal. What we were trying to do previously in the system prompt was to look at this function and explain it. Now we are automating it. We are saying that let's come to an agreement how to write these tools. And then if we all follow certain structures, for example, we always include some function description here. We always include types here in front of the arguments. We also specify what is the output type. And similarly here, we say that, hey, these two values are float, the output is dictionary, and this function is returning the full forecast JSON for the given latitude, longitude using API weather.gov. As long as these things are present as we write these functions, the auto formatter can automate that process and handle it for us. It can just go there, parse, and output something like this. It can say tool name add, because the name of the tool is add. Then it can say description. It can extract the description here, add two integers. So it says add two integers, comma. Arguments A int, B int, outputs int. So basically, this is a nice way to automate this process and also standardize. Now, for all these different tools, there is a very standard way of explaining those in textual format to the LLM. And you see, this is now coming from get forecast, and it's following the exact same structure. So it's a standard. And it says tool name, get forecast, description, return the full forecast. It's coming from here, and then input, output. So that's auto formatter. Now we can suddenly scale to hundreds or even thousands of tools with this auto formatter software. So now let's say we have lots of different tools in our company. We have lots of different Python files and functions, and we want to make LLM capable by introducing all those tools to the LLM when it wants to use them. And all we need to do is we need to use this auto formatter and pass all these functions, get the descriptions, and then from these descriptions, we can basically construct our system prompt. And this can be also automated using some code. And in the code, first we can start with some the things that we learned in the prompt engineering video. We can include like you are an AI assistant designed to help users and so on and so forth, and then few short prompts and all those things. And at the end, we can say you have also access to the following tools. And then we can just copy paste all these textual descriptions here. So automatically we are going from thousands of functions to a system prompt that is explaining each of those tools. So this is awesome, but then still there is a problem. It requires manual integration. So what that means is that I have this here. What manual integration means is that now let's say for the same use case, for example, let's say we all want to use a Slack API as one of our tools. You know, different companies are providing these APIs, so we can use them. And then we can write a wrapper. Basically, we can write a Python function to use call those APIs. We saw that how we write a function to get the weather forecast from some API. We can do that by relying on a Slack APIs. So now let's say we are company one and we write this wrapper, we call it a Slack tools. And then we use all our automation like auto formatter and everything to introduce these tools in the system prompt. Now, this is called a manual integration because we write a wrapper or a function to use those, rely on some external APIs, and then we integrate it into our set of tools by running it through auto formatter, get textual descriptions, and placing this as Slack tools somewhere in our code base. And this way, the LLM would be able to, and the generation piece would be able to use these things. Now, let's say company 2 wants to also do this same thing because this is a common use case and it's generally very helpful for LLMs. Now, in this case, company 2 also has to write their own wrapper, and they may call it something differently, like Slack integration.py. And then they have to manually also integrate that into their tools. And then let's say there are lots of different companies and they're startups. They each would manually integrate a Slack API as one of their tools into their chatbot. So it's still not as efficient. I mean, we were successfully able to automate this. Here, we were able to standardize this process of introducing tools to LLMs in the system prompt. But still, this integration part is not a standard yet, meaning that different people may write these different weather.py or Slack APIs. So now the problem of this setup is that it's not efficient. For example, all these different companies have to spend time writing their own implementation of a Slack tools or a Slack integration, and then they manually integrate them. So if there are n different companies, there would be n different integration. Now, the next topic we want to talk about is MCP, or Model Context Protocol, introduced by Anthropic. And basically what it tries to do is it tries to automate this process, basically go from this manual integration to something more standardized. So basically it's still a standardizing mechanism, but it's not happening at this level that we saw earlier, at this creating the system prompt level. It's happening at the integration level. So we'll go over that in the next video. Hello, everyone. Let's continue our discussion and focus on MCP in this lecture. In the previous lecture, we saw that in order to add tools, we have to do a lot of manual integrations. For example, if there are n companies here, and there are lots of different services and APIs out there, let's say M services and APIs, including our desire to connect certain tools to certain databases that we have internally, the total number of integrations would be n times m. And for each arrow is basically showing one required integration. So basically, if company 1 decides to use a Slack API, they have to write a wrapper or function. In the function, they would call the API, and then that function becomes part of their tool set, and they just keep it as part of their tools. So this was before MCP. Now, MCP basically what it does, it tries to simplify this manual integration process. Instead of each company manually integrating its service or API, it tries to simplify that. But let's see what that is. Basically, MCP was introduced by Anthropic on November 25th. And this is just the announcement. It explains that this is MCP and this is what it tries to address. And also some initial tutorial to get started. But basically, at its core, what Model Context Protocol is, based on their definition, is a universal open standard for connecting AI systems with data sources. So we'll see what that means. But basically, here, what it's saying is that it's an open standard, it's a protocol to connect AI systems which are on the left. For example, company one may have an LLM and they want to connect this LLM to certain tools or data sources. And data sources is basically where the company one data lives. It could be some databases and it could be in some other formats. But basically the idea of MCP is to simplify this process so we can easily connect our LLM or host to certain services or tools or databases. So what is the approach? Basically the idea is instead of each company writing their own wrapper on top of external services or APIs, why not the service provider writes some functions or some tools and then expose it as a server to the public? So basically the idea is, let's say company one wants to use a Slack. Previously, they had to write a wrapper. Company one had to write a wrapper. And in the wrapper, in the function, they have to call Slack API. Now, with MCP, what happens is that basically a Slack writes a bunch of functions depending on what they want to offer to the public. For instance, things like a Slack list channels, a Slack get channel history, and so on. And then they follow some protocol, which is MCP protocol, to basically expose them as servers. So what Slack does as a company is create these functions and then expose them as servers. So now these MCP servers can be called by people from outside, from like company one or any other companies, to send a request. And this server would simply send your request or company one's request to this function, get the response, and then send it back to the company. And the same thing happens by a company. Basically, they also need to create an MCP client. It can be their basically company one's host or IDE or LLM, or also tools. Basically, it's just a piece of software at the end of the day that creates an MCP client by following the same protocol. Now, this MCP client can easily send requests to this MCP server and get the response back, and then send it back to this software. So this way, company one does not need to worry about writing wrappers or writing functions on top of available services. Basically, company one never has to write any function to call a Slack APIs, like a Slack list channels, this and that. So that's the high-level idea of MCP. And here, basically, you can see after MCP, this is how life would look like. Basically, there are a bunch of different services like Slack, Google Drive, and so on. And then each of these services can create their own MCP server and then make it available to the public. For example, Slack can just create this Slack MCP server. Google Drive can create one or multiple MCP servers. We can also create MCP server by following the same protocol and connecting it to our database. And this database is basically internal to our company. But regardless, basically there are a bunch of MCP servers being created here. And now each company, depending on what they need, they can just send a request, get the response back. For example, if company one wants to use a Slack and let's say Drive MCP server 2, they can just send their request to these two servers and get their response back. So basically, automatically, this way, they can easily use lots of different tools that are available out there. They just need to be aware of the server that is offering that service send a request, get response back, and then move on with their with their generation. And you can see how now this part is simplified. We no longer need a lot of manual integrations. Basically, there is just one wrapper on top of Slack APIs, which is developed by the Slack team, for instance. And then every other company, whenever they want to use it, they would just call this server. They no longer need to create any function or any manual integration. So that's MCP. And then I also searched Google MCP, and here on their images, you can see there are a bunch of different images and visuals. And I found this in particular interesting because basically it's showing here a laptop, and this laptop is the host. It can be your LLM, it can be your LLM IDE, or you can think of it basically as client, MCP client. Now, and these are some other services that are external, for example, the Slack, like Gmail, Google Calendar, and so on. So what MCP does, MCP basically sits in between different laptops and different external services and simplify the process and make it a standard. So from now on, whenever any laptop and any service wants to get connected, they can just connect themselves to this MCP server, to this MCP protocol. So basically a Slack just connects here and then expose itself as a server. And then any client can also get itself connected to this MCP. And this way they can easily just deal with this MCP component instead of going over all different services. So I found that this visual interesting, so I just wanted to show you if it helps get the intuition better. Now, back to our lecture. Let's now see how the overall workflow looks like when we want to use MCP and create some tools for our LLM. So basically, there are a bunch of remote repository of MCP servers. These are the ones that are developed by external services or providers. They can be a Slack, they can be Git, they can be Google Drive. Basically, any service that they have already developed and a server for it. These are available, let's say, and we may want to use some of them. We may also want to implement our own MCP servers. Now, let's say we have some databases, for example, we saw in a retail store example. There might be questions like, where is my order? For those kind of questions, there needs to be a query to some databases that we have internally to understand where a particular order is. Because of that, we also need to write some MCP servers and connect them to our databases, internal databases. So those become our local MCP servers. We follow the exact same MCP protocol to create these servers so that everything is still, we keep it simple and consistent. So let's say we also implement 3 MCP servers and we have 3 wrappers or functions. We connect them to our database and then expose them as servers. Now, the third step is to introduce these tools now, which are a bunch of MCP servers to the LLM. And this is exactly when MCP shines, because we no longer need to connect this software, which we saw previously, with lots of different tools. All we need to do is we provide this just a text file or a JSON file. We call it servers.json. And then inside this, we can just list a bunch of servers that we want to be made available to our LLM or to this software. So for example, here we have MCP server, and one MCP server that we are including here is GitHub. And basically here we are just saying how to use it, how to use this server, how to send a request and get your response. So once this server.json is given to this software knows how to deal with all different services that are out there, how to call them, call their MCP server and get their response back. So that's simple. We no longer need to really change code in our code base or add new things in the software. All we need to do is we just write this software once to know how to deal with servers.json. And then from that point forward, everything should be fine. because software starts interacting with LLM, generating tokens one by one. As soon as the LLM generate that special token to use some tool, the software would figure out which tool the LLM wants to be used. It goes to its server. It finds the MCP server for that particular tool. It would send a request to that particular server, get the response back. And once it has the response, it would send it back to the LLM and continue the generation process. So that's simple. Everything becomes a lot simpler once we have just a bunch of local or remote MCP servers. And finally, it's very easy to maintain this system, because as we decide to add more tools, it's just as simple as adding a new, basically adding a new MCP server to this list and just including that. That's it. We don't need to do anything else. We don't need to change our software. We don't need to add any code or change any code. We just update these servers.json. Even if we decide to remove some tool or update tools, we can just easily come here and just make some changes. And as soon as servers.json is updated, the software still knows how to interact with it. So it can continue to rely on it and use it for sending requests, getting responses. And this should be 4. So that's about MCP. Before we wrap up this video, there are a couple of more things I want to show. First, we saw how LLMs know to output special tokens whenever we include in the system prompt that, hey, these are the tools that you can use. We saw this here, that if we provide something like this to the system prompt, in the system prompt and provide it to the LLM would know to some extent when to use which tool and how to use it. And it would just output those tokens, follow this format. Now, this is not always ideal. If we think of the original LLMs that were being trained, they were being trained on internet data. And we rarely have those kind of function callings on the internet data. It's basically a bunch of text and the LLM learns to use those. Now, because of its capabilities, it learns from the few shot examples that we provide or certain formats that we ask the LLM to follow, but it may not always be reliable or have high accuracy. And again, that's because if the LLM is not trained to call functions or do those kind of things, it may not be as accurate. So one thing that a lot of companies do is they fine-tune for function calling. So after they train the LLM, they also add some data to their data set, which has this kind of function calling whenever needed. And then they just continue training the LLM on that kind of data. And this way, the model would become more reliable into function calling. It's going to be more capable. It would have some idea about tools, when to call tools, what happens, how to follow the format, and those kind of things. So I also wanted to say that this is one direction that a lot of good advanced LLM nowadays are also being trained on. Basically, they're fine-tuned for function calling. And that's because we want the LLM, basically, it increased function calling accuracy and reliability. And again, there are a bunch of different documents how to do it. This one is published by OpenAI, and it's just an interesting read. If you are interested, it says how to start training your LLM and then fine-tuning it on function calling. So in case you want to take a look at this. The other thing I want to share is that we talked about MCP and we saw like there is this protocol and create these MCP servers and basically how to basically write some tools and let the LLM know about those tools. In practice, we really don't need to implement a lot of things. A lot of those are already implemented for us. For example, here I have LangChain open, and LangChain is just a library that simplifies a lot of LLM developments. And you can see in LangChain, basically, there is this tools section. It gives an overview, how to include functions, Python functions, and add them to some LLMs and expected arguments. So it is also an interesting read. But what I want to show is that in practice, it's very simple to introduce tools. All we need to do, for example, if we decide to use LangChain for this purpose, is that we import tool. And then if we have a function that we want to use it as a tool and introduce it as a tool to the LLM, we just add this decorator, add tool. That's it. So this way, basically, later, during the generation process, when we are generating tokens from the LLM, and when LLM requests some output that special token that it wants to use, it's already aware of that this is one of its tools. So it's very simple. My whole point is that there are a lot of details in the theories, but when it comes to practice, most of these are already implemented, and it's just a few lines of code that are needed to add new functions, introduce them to the LLM, and make the LLM more capable. And whenever the LLM wants to use it, or that particular software wants to use it, it's just as simple as this: multiply.invoke, and multiply is this tool. And basically it invokes it with the arguments that the LLM asks for. So you can take a look at this to learn about the details. But again, it's generally very simple to write tools, introduce them to the LLM, and make the LLM and call them, execute them by using .invoke. And also, this is another documentation here for how to do tool or function calling. So I also wanted to show this. If you are interested, you can go over it. Again, here it's just explaining how easy it is to write new functions and then specify them as tool, and then later invoke them whenever needed. So once we have those tools, see here it says my tools are add and multiply. And when it's creating the LLM, it specifies the model, and then it says LLM bind tools. Now this is a new LLM, but it's already aware of all the available tools, and it can invoke them. So yeah, just take a look at this. It may help a lot, especially for recent developments, like at the application level, which a lot of times we want to rely on these additional functionalities or tools and use some LLM. These libraries are very helpful. So that's it. And this is also another page. It shows some options to use different tools. And it's interesting because you can see there are a bunch of available tools that we can just use with very small number of changes and codes and lines in the code. So for example, here we have search, like Bing search, and like Google search, and a bunch of other searches. And we have code interpreter, we have productivity tools, and so on. So most of these are available to be used whenever we want to use these libraries to build some applications. Now, that's it. I think I covered everything for tool, functions, tool calling, and MCP protocol. Now, in the next lecture, we are going to switch to the next agency level, which is building multi-step agents. Hey, let's continue talking about different agency levels, and the focus of this lecture would be on multi-step agents. In the workflow, we saw that how we can create a workflow like this, and then whenever a prompt comes, it goes through this workflow, and then the information would flow according to that, and then finally we would have the response. Now, workflows are very powerful because they can handle complex tasks through this predefined plan. However, they have two major limitations. One limitation is that they are fixed, meaning that this execution plan or this flow of information is something fixed and it's predefined. So that is not ideal. The second limitation is that this workflow, they don't have access to live information. So no matter how complex this workflow is, if we ask a question like, how's the weather today in San Francisco, it would still fail because they really cannot get like live updates or live information, even if the workflow is very complex, or even if there is like mechanisms like reflection employed in workflows. So this access to live information can be easily solved by combining workflows with tools. We saw that how tools work in the last lecture. And basically the idea is we can still come up with nice predefined workflows depending on our task. And then we can augment each LLM with tools. So when the prompt comes here, still the same LLM continues to process it, and then the information would continue to flow according to this plan. But now the difference is that all these LLMs are given system prompts that specify which tools are available and they can use. So they can use different tools, get their information they want, and pass it to the next step. So when we combine workflows with tools, we are fixing the live information limitation. And now we have basically access to live information. We have access to external services and APIs. But still, the same problem that we had before with workflows is that it's fixed, meaning that this flow of information cannot be changed depending on the input prompt. Now, this is exactly what multi-step agents trying to fix. Basically, the idea is to go from this fixed workflow to a dynamic workflow that is determined at runtime. So this is the very high-level definition. And basically, you can think of it as we are giving autonomy to the agentic system for decision-making. We are not going to predefine something for it. We are just letting the system, the agent, decides how to, what are the next steps. For example, an agent may analyze a customer's message, decide to retrieve information from a database, then generate a response. And all this can happen with basically without having a very fixed workflow. This can happen at runtime. And dynamically, the agent can decide what are the right steps. So again, the high-level idea in agents is to plan, act, and then adapt. Basically, we are giving autonomy in decision-making or planning to the system. So these are the three main things that in this setup in agents, the agent is expected to perform. The agent understands the current situation and the goal. This is based on the prompt and any additional context that we include in the prompt. So it understands what is the request, what is the final goal, and then it basically uses all those information to plan. And then the next thing is it plans. Basically, it tries to come up with a sequence of actions that can go from the current situation to the goal. And then this plan will be executed. And then it would decide what are the right tools to use in real time. And after it executes those plans and get the outputs from the tools, it then reasons and handles errors or tweaks the plan as needed. And basically, the agent keeps iterating until the goal is met. So we can represent it like this. The agent is here again, as always. And then prompt comes in. The agent has access to an LLM, and it has also access to tools in order to execute some tools when needed. And then it has also memory. And the tools are basically, these are different tools such as web browsers, APIs, databases, Python execution, file systems, or any custom function that we saw in previous lecture. And memory is simply, basically, we just keep track of all the interactions and all the outputs from the tools, and we keep them in the context. And this is useful so that the agent can iteratively improve its response and plan and adapt. So this is all very abstract. This is just a high-level workflow of agents. Now let's make it more concrete and detailed. So how agents really plan? Agents work in a continuous cycle. They have typically, we can think of it as three components: thinking or thought, acting or act, and observing. So there is this loop here. Basically, the agent thinks, or some component that the agent has access to thinks. Then some actions is happening. And then from the action, there is an observation phase, which will reflect. And then those observations are passed to this think module so that it can think again and plan. For example, the thought can be something like, I need to check the current weather for New York. So this is a thinking. And then as a result of that, an action is required. Something like this structured format. Action, get weather, which is one of our tools, and then the arguments. Now, the action module would parse this, run this, get the output, send the output to observation. Now, the observation would see something like, I need to check the current weather for New York, action, and then right after this, it would see the actual output from the tool. And this whole thing is now passed to the think module so that it can think again and plan whether more steps are needed or we are good to show the final response to the user. So let's just think a little bit more deeply about these three components. Basically, during the think stage, the LLM plans and decides what the next step should be to solve the task. This is where the actual reasoning happens and also the actual planning happens. During this process, the LLM breaks down complex problems into smaller, more manageable steps. It can also reflect on the past experiences based on the tools that were previously called. And also, it continuously adjusts its plan based on the new information that it's getting. And these are different types of thoughts that can happen at this stage by the LLM. It can happen, planning can happen. There could be other types of thought like decision making, reflection, goal setting, and so on, and also setting the priorities. So this step is very important, and it's basically the core of the agents. And this is, as you can imagine, is happening by the LLM. Then we have actions. For actions, basically the LLM requests to use a certain tool with some arguments, and then the agent takes care of it. It basically parse the requested function, and then it takes an action by calling the tools with the provided arguments. So this is the action step. And then observation is basically when we incorporate feedback into our memory, and then we let the LLM adapt again. Basically, the LLM reflects on the response from the tool, and these are the three steps. First, in the observation, we collect feedback, and this is basically just receiving tool execution results and checking if the action was successful or not. Because these are important, because sometimes the actions are not necessarily successful. For any reason, it may fail, and we can include those as the feedback and then pass it again to the think module so that it can figure out why there was some failure and perhaps request more actions again. So during observation, we collect the feedback, whatever the results from the tools are, and then we append them to integrate this new information into the existing memory. Basically, we append everything and include it in the context. And then finally, the LLM now can use this to adapt its strategy. It can update or refine subsequent thoughts and actions. And these three steps are happening in a loop. Basically, this is the loop. It just keeps happening until at some point the LLM believes that it accomplished the task and it has the final output or response to show to the user. So this is still a little bit abstract. So let's see how these three modules really translates in practice. So basically, this continuous loop in practice, it's just it combines reasoning at its core. It's combining reasoning and acting. So this is the loop when we translate it to the LLM and agentic system world. The prompt comes here, which has the system and user prompt. The LLM reasons and processes the prompt, and then requests for some actions and send it to this environment. And then this environment would execute those actions and then get some feedback and then return those feedback to the LLM. So this is the actual loop until at some point, this whole agentic system decide that the final result is ready. And basically all the rules and guidelines that we just talked about regarding the loop, and these are the three steps: observe, collect feedback, and everything. Basically all of those can be integrated into the system prompt. So you can think of a system prompt like this. I took this screenshot, and you would see different variations of system prompt. But again, the idea here is just to show that all of these multi-step agent workflows can be really described in a system prompt, and then the LLM would know how to create, how to think, and how to iteratively try to improve it. So a system prompt here is: you are an AI assistant designed to help users efficiently and accurately. Your primary goal is to provide helpful, precise, and clear responses. You have access to the following tools, and this is the tool. And then here is basically the part where we are defining that we want you to operate in a multi-step, as a multi-step agent setup. Basically, we say you should think a step by step in order to fulfill the objective, with a reasoning divided into thought, action, observation steps. that can be repeated multiple times if needed. So we are exactly describing the process in the system prompt. And then here we say about the reflection and collecting feedback, we say you should first reflect on the current situation using thought, and then your thought. We are giving it very specific structure to follow. So thought, and then your thoughts here. Then, if necessary, call a tool with the proper JSON formatting, and then follow this format action JSON blob, or print your final answer starting with the prefix final answer. And this is when you want the system decides to stop this iteration and show the final response to the user. So this is how really in practice these multi-step agents are working. Still, we have this agent, which is just a software. It communicates with the LLM and some tools, and then the LLM is given the system prompt that it needs to follow this multi-step setup. All right, so we saw multi-step agents, and we saw that in practice, it's just a loop. But these are all high levels. There are different patterns and different frameworks or techniques that we can use to make this happen. And over the years, there have been multiple papers, and they were proposing different ways or different paradigms to make this plan, act, adapt happen. So this is just a small but not comprehensive list. React, reflection, and some other methods. And this list is probably more. React is probably the most popular one to make this plan, act, adapt happen. And so we'll briefly go over React, reflection, and these two. And then after that, we would basically wrap up this multi-step agent and switch to evaluation. So React, basically what it does is it's a simple prompting technique, which combines reasoning and action. Basically, in their paper, they're saying that they're adding reasoning and act in a loop. It's just a loop, and then it has two steps. Reasoning, which traces, help the model induce, track, and update action plans. And then is the act stage, where actions allow it to gather additional information from external sources, such as knowledge base or environments. So, and this is from their paper. Here I have their paper open. It was published in 23. And they're just using a prompting technique to make this multi-step agent happen, or basically creating this multi-step agentic systems. And they are following a certain way of creating this system prompt and then showing different examples to interleave thoughts and actions and observations. And they're also comparing it with different other setups, like a standard COT, reason only, so only thinks and then it answers, and also act only. So it requests for some tools, it see the observation, again it requests for some tool, see the observation, and then finally it shows the final output. And basically the difference of this setup and their React setup is that they're also adding a reasoning step. So at each step, the model would reason and think, and then it would request for some tools. So this is an interesting paper. It's very simple at its core, but it's very also novel in a sense that it works quite well when we follow this approach to build this loop that we saw here, to build this think, action, observation loop. So back here, so again, they're following something like this. They give a system prompt to the model, and then the model would be capable to follow something like this. This is one example output from the model. It just reasons, and then some actions are called by the agent, and then the result of this agent tool call is going back to the LLM with this observation. So again, after this observation, the LLM think again and plans and request for more actions. Here it says do more search. And then again, we have observations that is the result of search, could not find these, similar, and so on. And then again, it would think based on that. And you can see based on all these contexts, now thought 3 is LLM is thinking that front row is not found. And that's because the observation is that could not find. And then it says, I need to search front row software. And then it requests again a search tool call with a new updated prompt, with the new updated query. And now this time, the observation is basically front row is a discontinued media center software. Now, again, it thinks. So at this point, basically, it has some good observations. So then it's ready to produce the final answer. So then here it says, so the answer is, and then Act 4, finish keyboard function keys. So I took this screenshot from their paper. They have a lot other different examples and more details about, and also evaluation, how it's compared with in different models and so on. So it's an interesting read. And basically, it's one way to make this multi-step agent happens. Now, there are also different papers after that. I mean, there is this reflection is basically based on linguistic feedback. So the idea here is that we improve agent through self-reflection by turning feedback from into a natural language. So basically, the idea is that whatever the feedback is, we use the LLM to convert it to a natural language. And then we use that and that summary as a context for future attempts. So basically, next time that LLM wants to think, it would just go over that the natural language feedback or summary. And it has some similarities to React. It has also some differences. And again, I have the paper here open. It's interesting to take a look. And it's also comparing this method with different methods. But basically, the core idea is to convert the tool's output, which can be, let's say, when you run a tool call, you may get some errors or failures or some warnings. And then an LLM would go over that and convert it to a nice summary in a natural language. And then that is used as the observation and passed to the LLM again. This is another way we can follow to build our multi-step agent. And there are more examples. There is this Revu. I don't know if I'm pronouncing it correctly, but basically the idea is that they are proposing a modular setup. They're saying that instead of having one LLM to perform both reasoning and observation, basically they are separating these two and allowing two different models to do these different tasks. So basically it detaches the reasoning from the external observations. And you can look at the paper again here. I think this is the one. Yes, they are proposing 3 components: a planner, a worker, a solver. And they're saying that this setup works better compared to React. I think they have also they are comparing it with React and saying that Revu is working better, by following this setup and having a more modular setup. And here they have a nice comparison between their modular setup versus the non-modular setup. Basically, one that reasoning and observations are happening by handling by the same model. And then again, there are more examples. There are more advanced examples. This is another paper called Tree Search for the language model agents. And basically the idea here is that, I have it in the lecture too. The idea is to run some sort of search, like a BFS search, within the environment step. So this way we explicitly perform exploration and multi-step planning. It's basically a more accurate way of figuring out which plans is better. And this is an interesting read as well. It says that we can start with something and then we can run BFS or some search algorithm to see which plans seems to be working better and has a higher score. So yeah, just wanted to include this here and say that there are lots of different papers exploring different directions and different search strategies to create multi-step agents. But at the core, they all are doing the same. They are basically following something like React. They are having different components, and then all of them are put together in a loop so that they can think and perform some actions and then observe and then think again. Now, before concluding the multi-step agents, let's quickly compare between workflow and multi-step agents now that we learned about both. They have differences in different aspects. For example, in terms of predictability, workflows offer predictable and more consistent outputs for well-defined tasks. And that makes sense because for tasks that we can easily define it and come up with some predefined path, it usually works better and more consistent because the LLM does not have to now plan or come up with some reasonings to plan. We already know what predefined workflow works well for those kind of tasks, and we have created those. But agents are better when we want more flexibility. And basically, we want the model to make decisions autonomously. And then we have also adaptability. Agents can adapt to new situations, but workflows not. For example, if there is a question and if the customers has a very unique question, then workflows may fail because they have this predefined path. But agents, they have autonomy, they can plan and make decisions at runtime. So this is a quick comparison between workflows and multi-step agents. There is also an interesting article here by Hugging Face, which compares agents versus workflows. And basically, there is also another article here, which is saying that there are differences between workflows and agents. And then a lot of startups that are advertising their product as agents are, in fact, AI workflows. So this is also an interesting read. That's also a good sign because it shows that a lot can happen by just creating AI workflows. So yeah, this is also another article I wanted to show. Now, the next thing that I have here is when to use multi-step agents. Basically, the autonomous nature of agents means that they have higher cost, and also there is more potential for compounding errors. So we have to be careful. It's not necessarily always better to use multi-step agents compared to workflows. And also the other complexity with multi-step agents is that they are challenging due to their dynamic nature to implement. So a lot of times their output can be unreliable, they can be illogical, or they may stuck in some infinite loops and so on. So to answer this question, when to use multi-step agents, in general, if a problem solution is well understood and repeatable, so in those cases, constraining the agent to a predetermined fixed workflow is usually more effective. On the other hand, when the agent can be, when the problem is not well understood, or it may have like very different range in terms of different questions may come, then agents might be more suitable because agents can be used for more open-ended problems and also for more difficult problems, which it's not easy to predict the number of steps or the exact workflow ahead of time. So in those cases, usually agents work better. And then some common examples where multi-step agents are used is basically, for example, in coding setups, where we want an agent to actually go and solve some software development tasks. Because in those cases, basically, we cannot really come up with a workflow. The agent needs to come up with some planning, then execute those codes, and then write some codes, execute those codes, and then then run those codes and run some tests on them. And then depending on how those tests turn out to be, then the agent has to, or the LLM has to come up with a better plan. So coding agents are typically good examples to use multi-step agents or even multi-agent systems, which we will cover shortly. The other example is robotics and autonomous navigation, and that's straightforward because in those scenarios, we also need there is no predefined path to define. Another example which multi-step agents are used frequently is when we are dealing with a structured information synthesis. And a good example is when we want our agent to do some research on some topic. So we saw on ChatGPT, there is this tool called Deep Research. And that's basically when you want to learn about some topic and you want this agent to go and explore the web and create a detailed report about that particular topic. So those are also good problems and good fit for multi-step agents. All right, so that's it about multi-step agents. We have some coding examples in project, and then there we will practice how to really create some of these workflows and use them. So yeah, just wanted to say we have some good coding practices there. And then the next thing I want to switch to is the next level or the final level of agency, which is multi-agent systems. So let's go to multi-step agents here. Basically, this is going to be brief because we already learned about all the key components. But basically here, the idea is the motivation is that a single agent may not be capable. For example, one agent may fail or move in some incorrect directions. And because of that, more agents can probably correct or validate, they can validate each other. And in multi-agent systems, we use multiple agents, and they work together to complete the task. And this way, the hope is that it's going to be more reliable. And this is going to be some visual explanation of it. We have typically there is a manager agent. This is responsible to coordinate between different agents. And then it has, of course, access to one LLM to reason and think and plan. And then as soon as this manager agent starts planning and talking with this LLM to know what are the right agents to activate, then it would start interacting with those agents. And those agents by themselves are like full multi-step agents. They can do something for you end to end. For example, if we look inside this web search agent, it would still look like something like this that we saw. It has one LLM, it has tools, it has memories, and there is this continuous loop. So multi-agents setups are also very powerful and provide the most agency to users. And there is also some challenges that I want to point out. In practice, building multi-agent systems are not easy. A lot of even advanced labs or companies are building these systems with a lot of caution and a lot of engineering efforts to make sure that the system would work and is reliable. Some of the common challenges are coordination, because now different agents have to communicate and share their results and share their plannings also. So it's not, coordination can be one challenge in general. And memory management, because all these agents have their own memory and then they're not really seeing the memory from other agents. However, the memory from other agents might be useful at some point. And then they're also facing these compounding errors, because again, one error would compound because these systems are built in a like kind of loop. And then whenever something is wrong, it would just compound over time. And now that it's multi-agent system, basically each agent might have these compounding errors. And as they are working together, the errors may even amplify that, and the error might be even more. So I have two links open here. One is from Anthropic. The title is How We Build Our Multi-Agent Research Systems. Basically, they are hinting us that the research system is based on a multi-agent setup. And they have a very nice article about how they are building it and what is their system look like. There is this lead agent, and then there are different sub-agents like search sub-agent. And in parallel, they are just starting sub-agents, search sub-agents to do exploration and collect information. And then this lead agent would just orchestrate all of this and then return the final report. So it's an interesting read. And also it's a very interesting use case that is relying on multi-agent setup to serve users. So this is a very interesting read. And then here they have the process, the system process, which starts from the user. They send it to the system, and then all these steps that are involved. And then here is this iterative research process. So it's a nice read. And also OpenAI here, they have open source the RIP research prompt rewriter. And if you just look at these, they're also hinting us that they might be using, and this is their prompt, the system prompt, and some coding. Basically, this is also hinting us that their deep research system is also based on a multi-agent setup. You can also take a look at some of these. They could be interesting. And finally, here is a nice guide, a practical guide to build agents published by OpenAI. So this is also an interesting read. It talks about all the challenges that we may face, different use cases, and which agent is more, which agency level is more appropriate. So yeah, they have they talk about different models, tools, instructions, and how to select your model, defining tools. So this is also a very good guide. Now back to our lecture, very similar to what we saw in tools, that they have to communicate somehow with some protocol. We have this similar need when we are building multi-agent systems. Ideally, we want to have a standard protocol so that different agents can communicate. If we do that, basically, we would have the same benefits that we saw previously with tools and MCP. And then the good news is that there is also a protocol for that. It's called agent to agent. And it was announced by Google. And this is their article in April 25th. And they're talking about all the benefits and need and different ways. And also they go over the design and principles and how this A2A works and how different agents can really speak with each other and discover each other. So this is, again, another way to define some protocol so that agents can talk with each other. And again, one thing I want to share here is that there has been other proposals also previously. And there are lots of different works around what is the good way and a standard way for agents to talk to each other or tools to talk to each other and so on. And this survey might be interesting because it's talking about all different proposals like MCP and A2A and what each of those are handling, like MCP here, A2A, and also other different proposals or protocols that are available. So it has a very nice and comprehensive discussion around all these agent and protocols. I suggest you take a look if you haven't seen, and they have these nice timelines. So that's it. That's all about A2A protocol. It's simply an open protocol that AI agents can communicate. And finally, the last thing I want to talk about is about evaluation. We learned how to build these agents, and they are very capable. But very important question: how can we really compare these agents? So I included some common metrics here, but again, there are very good surveys with lots of evaluation metrics out there. But a couple of very important metrics that we generally want to take a look when we are evaluating different agents is, one is token consumption. Basically, what is the average token usage per request? And that's important because it affects the cost per request. When there are more tokens involved in the thinking process and accomplishing the task, it means that there would be higher cost to accomplish each task. And it's very important because ideally we want agents that are more capable but less expensive. Then there are other metrics like tool execution success rate. This is important because a lot of times if the system is not set up correctly or the LLM is not good, there might be a lot of failures in executing the tools. And also there are other metrics like observability, like how to observe if something goes wrong, how can we figure out which component is causing it, how can we fix those. And finally, task success rate. So if we have a good benchmark with certain tasks, let's say software development benchmarks, and then with correct solution, basically this is also a good metric to measure, because at the end of the day, what we want is whether we want to know if the agent can really complete a task or not. And similar to LLMs, there are different leaderboards for agents. I have one open here. You can also take a look. There are leaderboards and there are different agents listed. So I think, let's see. So yeah, they have some just list and in different domains, and there are different metrics. So you can also take a look. Also different, banking, healthcare, insurance, and again, they're just leaderboards. And as we are getting more into agents and companies are starting to build these agents, it's important to have a leaderboard so we know in different tasks how capable these different agents are. So it just exists. Basically these leaderboards exist. That's it. And finally, before we wrap up, I want to briefly talk about the frameworks. And I took this screenshot from this website. And then they are just giving an overview of the AI agent stack and some of the frameworks that can be used to build agents. So again, the whole point is that there are lots of different tools and frameworks out there. We can easily rely on those to create these agentic systems. In practice, it's usually simpler compared to theory. There are a lot of theories involved. In each of these papers we saw there are lots of details, evaluation. But when it comes to implementation, usually these libraries like LangChain are very easy to use, and we can implement these different multi-step agents, multi-agent systems easily. And there is also one, OpenAI has also this Agents SDK. It's very easy to use. And some examples here. I know that Google has also one SDK to build agentic systems. So yeah, these are lots of different libraries, and some of them are open source. Some are give you more flexibility. Some give you less flexibility. But we'll see also some examples to use these frameworks to build some multi-step agents in our project. So that's it. That's all I wanted to cover for week 3. So yeah,